Yes.
Great. Okay. I'll go ahead then. So good morning, everyone. My name is Charalampos Katsis from Purdue University. Today, I'm excited to talk to you about our work, NEUTRON, a graph-based pipeline for zero trust network architectures. This is joint work with Smart Information Flow Technologies in Minneapolis. So what is the motivation here? So throughout the past decades, we have seen an emergence in computer networks, like the growing very large and complex communication infrastructures that emphasize on the ability to communicate with everyone, as opposed to only one that needs to communicate with. So this flexibility enhances communication efficiency, but opens the door to adversaries to probe networks without authorization. Resources actually on networks without authorization. So NIST has came up with a very interesting document in 2020 that talks about this zero trust architecture and potential ways that one can start thinking of employing it. So it describes approaches to prevent the attacker's lateral movements and control access to resources. It has been developed on the premise that only authorized and authenticated actions may be executed on the network, as now we assume an adversarial presence. In other words, no trust can be assumed unless explicitly specified. One way to support such fine-grained access control is through a technique which we call micro-segmentation, by which a network device, say that we have a gateway or a firewall, acts as a policy enforcement point, protecting a resource or a group of resources. But if we can minimize permission to what is absolutely necessary to ensure normal network operations, we can avoid unnecessary permissions and therefore implement a least privilege policy. But then this is easier, easily said than done, more easily said than done. And then the problem is that to achieve such a thing in terms of access control, the network administrators need to define and manage detailed network permissions, which is very error-prone, daunting, and time-consuming task. In addition, the communication requirements of assets that exist and live in the network, like cloud components, servers, applications, and of course, our users need to be very, very well understood. In other words, the admins need to determine who needs to access what on the network and for which reason. Then, of course, the admins need to formulate the network access control policy and that specifies which users may interact with which assets. And of course, somebody has to log into PEP and define the rules in a very technical level. So what we do in this work, we propose NEUTRON, which is a policy framework that supports a comprehensive policy generation pipeline that spans all the way from specification to testing and deployment of policies in the networks. So in a nutshell, what we do is that we propose and implement a network-aware policy specification framework that captures realistic network policies using patterns, which we are going to talk about, and represent them in graphs. So this specification becomes an input to a policy generator that traverses the policies and compiles different sets of rules, which are finally deployed on the network. As part of this work, we also propose the Security Policy Regression Tool that utilizes the semantics captured in the specification to perform a thorough testing and ensure that the applications can perform their mission successfully, while also supporting claims of a least privilege policy. Also, the tool is able to perform a change impact analysis, which we are going to see later on. Finally, we are going to talk about evaluation and future work. Let's start from the policy specification. So our framework divides the policy specification into two parts. The first part is the static policy, which includes includes things like application communication requirements, task-based, the high-level task-based access control, and then on your right is the local policy, which composes of another access control model defined by the administrator and other configurations. Why did we separate this framework into two parts? This is because we want to differentiate cross-organization patterns from local policy requirements. Let's see some as an overview of the graph. So the first one is our novel communication requirements graph, which captures communication patterns between different network services, and it is independent of the underlying network topology. This is on the static part of the policy. These requirements become critical for testing the resulting policy for correctness and ensure that only the required communications are allowed. So in this figure, all nodes fall, the nodes fall into two categories. So we have the classes of objects like user laptops and the internet, and we have also specific instances for let's say servers such as the email server. So here what we see is a combination of task-based access control and role-based access control. So the RBAC graph groups permissions into an object-oriented design to capture common access patterns, and it is defined by the local administrator. However, rather than mapping, so this is the familiar RBAC model from the security literature, but with a slight change. Rather than mapping roles to permissions, we map roles to tasks from the task graph. The task graph is associated with the permissions for access to resources. The task graph parallels the familiar RBAC graph, but it is separated to represent to separate the cross-organization patterns from local policy requirements. Now, as you can understand, the communication requirements graph provides a very concise insight on the communication needs of the services. However, the realities of actual real network protocols add an extra layer of complication that creates the need for a separate graph that we call the protocol sequence graph. So many protocols are uniform, but some other use asymmetric paths that impact the enforcement of the security policy on the network devices. For example, connections to an FTP server are initiated on one port, but the file transfer happens on another port. So the graph captures the communications sequence to ensure that the resulting policy includes all the necessary ports. It also models protocol events that must happen in a sequence, which is impacting how to enforce the policy on the network. An example of a local policy graph now is the network topology graph, which is represents the underlying network topology that is under administrator's control. Nodes correspond to host and network policy enforcement points like switches and firewalls. And then the model types each PP policy enforcement point because different types of enforcement points have different capabilities to enforce a policy. For example, one might consider an inexpensive PP, which can only support a very small number of security policies. And then therefore, our pipeline needs to take this under consideration. Now, for the policy generator, it gives it the basic elements available for policy enforcement. Now, due to time limitations, we don't have the time to go through all the graphs of the framework, but we discussed them in detail in the paper. A key takeaway that I want you to have is that the graphs provide a flexible abstraction to model and reason about policies. The set of graphs allow us to express a variety of security patterns that vary in policy complexity. The communication requirements graph represents relatively static policies, and it is best defined that it shows how services interact, and it is best defined by the people who create those services, not by administrators. Then on the other hand, we have the standard protocols like FTP, HTTP. Those are very extremely static, and those are best defined by network protocol developers. In other words, in our framework, we envision that the security policy enforcement needs to be shared and validated by experts, so that we also avoid errors. In other words, so admins needs to determine how to satisfy their local security requirements with the security policy building blocks provided by the developers. Here, what we see is an example of a network of a policy specification in our framework. So in NEUTRON, the designers specify those policies in Java programming language. In other words, the policy itself becomes a software. We discussed the policy in terms of graphs for clarity. Note that NEUTRON provides code that converts the Java code into graphs for easy inspection and debugging. This is illustrated in the figure on the right. For example, you can see the green area denoted by A. The policy defines network applications, two network applications, one for Git and one for the backend database. Then it specifies that the entities should talk with each other through HTTP protocol. At the compilation time, the generator will instantiate those objects and associate them with the real machines in the underlying network. In the case of users, rather than specifying the policy for, say, Bob's and Alice's laptop individually, we create a pattern specifying that each user gets an arbitrary laptop, whatever laptop. See, for example, the blue area denoted by B in the figure. The generator will determine the unique sort of permissions that are associated with these laptops based on the roles assigned to the user. For example, let's say that the engineers must access the Git server and Bob is an engineer. Then Bob's laptop will receive access permissions to the Git server. What comes next is the policy sanity check. So the generator will receive the specification and perform a sanity check to a sanity check to ensure that the specification complies with any specified constraints. What are examples of those constraints that we support? Is, for example, the separation of duty, where a set of permissions cannot be assigned to, let's say, the same user. It could be conflicting permissions that are inherited from different roles. And finally, NEUTRON supports simple cardinality constraints that limit the number of users who will receive a particular permission. So we have the policy. Now, after the policy specification check, and we have like a verification of those constraints, we combine those graphs to generate the network-wide security policy. Specifically, we analyze the patterns in the input graphs to derive the network entities that may communicate and how to communicate. This is essentially what we call the unified graph. And then to do this, we use the software engineering visitor pattern. And what is the visitor? Visitor is a recursive function that traverses the policy graphs and generates this unified graph. For example, the generator instantiates a host for all user laptops by traversing from the user laptop task to all class and then users that inherit from there. In the paper, we provide the algorithm for this visitor algorithm. Finally, the graph, the unified graph is translated into firewall rules. In this example, we see PF rules. So in the final step, we see those the generated rules for an arbitrary router in the network. Now we have generated the policy. The next part would be the testing part, which is why we have SPRT. Another so SPRT utilizes those semantics, the graph semantics that is captured in our framework to ensure that users and services can accomplish their mission successfully in a least privileged manner. Regression testing the security policy will detect unnecessary permission or inconsistent permissions before their deployment on the network. So the functionality is twofold. One is the policy verification and then the change impact analysis that we mentioned before. What happens in the network-aware verification? So SPRT will generate an exhaustive set of test cases. And then those test cases are composed essentially of proto packets that correspond to real network packets that need to flow through the network in order to satisfy the communication requirements. So the core functionality, the core policy verification functionality is based on our proposed rule set aggregation algorithm, and it has achieves 7 detectors. The first detector is the reachability testing, which essentially ensures that given the communication graphs, can my entities talk through the specified communication protocols? If the test fails, then SPRT will provide a lot of conceptual information. So why the test is generated and where exactly does the failure happen in my network? Sport yields an error when the device in the routing path it gets denied because it's supposed to be a legitimate communication. It checks also for stateless rules, which are very common in the firewalls. In case you have to stateless rule and you expect your destination to reply, there must be another rule in place to allow the responses to pass. So sport checks accounts for that as well. In the case of multiple paths, sport checks the rule set's consistency across the PPs present on those paths, and what is more, it also identifies rules that have not been triggered, that have not been triggered during testing, and therefore we can safely eliminate those rules without impacting the overall network policy. So sport yields an error when a packet is allowed. It's allowed by default, as this contradicts the general idea of zero trust. And finally, sport also confirms whether the generated rule sets correctly reflect only the necessary communications in the network. So here you can see we have two colors. One, it's the red, which represents errors, and then the yellow, which represents warnings. Errors refers to problems in the network topology that violate the communication requirements. In a sense, you cannot deploy such things because things will go wrong. But warnings refer to potential inconsistencies. One guy can go ahead, deploy those rules, but somebody has to check manually. Now, for the policy change impact analysis part. So here what we do is that in our framework, because we are using graphs, or it organizes permissions into patterns and then relationships between those patterns to inherit permissions. And this inheritance structure can be thought of as a tree where resources are forming the leaves and then the users are at the root of the tree. So Sport will build up a bottom-up hash tree for each policy specification through a method similar to the Merkle tree construction. Such a technique allows us to very efficiently identify changes and the entities that are impacted by those changes for any two arbitrary policy sets. This is very important because usually when people go in the networks and change the policy, they don't really know the impact of such policy change. And then we, receive mails, oh, something went wrong, the service is not responsive and stuff like that. So here we see an example that of Sport reporting changes, like a very simple example. The connection between the Git task and the software developer was removed, as you can see, and then instead the Git task is now mapped to the base role. The software developer and the researcher roles inherit the base roles access permissions, and that can access the Git task. Now, since Alice and Bob are mapped to the software developer and researcher roles, they can access the Git task. Ultimately, for nothing changes for Alice, as you can see, she just receives the same permission for a different part. But for Bob, actually, it's an extra privilege that he did not have before. So this is an example of an output that we obtained through our experiments. So the tool highlights the three different types of inconsistency by using a three-color labeling system to represent the event severity. For example, you can see that communication requirements, satisfied requirements are reported in green, warnings are in yellow, and errors in red. So here what we see is a snippet of some performance evaluation that we carried out. For all experiments, the policy generator enforces a defense, which means that all rules pertaining to communication endpoints are deployed in every PP on the path from the source to the destination. Therefore, we evaluate both Sport and the policy generator in the more stressful settings with respect to the policy placement. This table lists the execution times of the policy generator and Sport separately to highlight each component's performance. Both the policy generator and Sport scale with reasonably large networks. For instance, with a network with more than 20,000 nodes, the policy generator produces the rules in about 13 minutes, whereas Sport performs the regression testing in about half an hour. The size of the network, as we increase the size of our network, both in terms of users and PPs, so that the execution time and the memory space required by our current prototypes. Since the policy generator enforces a difference in depth, the number of rules grows exponentially, as you can see, with the number of hosts and nodes, and of course, PPs. Especially if you have more complicated networks where you have multi-path propagation between two endpoints, the network's complexity increases. And of course, NEUTRON has to examine all the possible paths to ensure that the policies, the requirements are satisfied. So let's conclude our presentation with some future work. So we plan to extend NEUTRON with capabilities to automatically determine the communication requirements of applications and also users and perform some network traffic analysis. Characteristics of real network traffic can profile common and rare communications and optimize the rule placement in those policy enforcement points. Traffic analysis can also serve as input to automatically determine the communication requirements and other graphs of our framework when those requirements are unknown. And as you can understand, this is very common because usually when vendors ship software, you don't really know what is happening with the software. Where does it communicate? Which resources does it need to work on and stuff like that. So we say, how about we come up with those requirements ourselves automatically in a systematic way? Finally, we envision NEUTRON to being reactive to underlying physical infrastructure failures and maybe automatically reconfiguring the network in real time based on demands. We are additionally investigating ways in which NEUTRON can react to real-time cyber attacks. So for example, when I'm under attack, what should I do when I detect the attack? So for example, you can have a couple of decisions, let's say, and then those decisions could be, for example, host isolation or limiting the network traffic, passing the traffic through an intrusion detection system and stuff like that. But when you are under attack, what is the best possible solution that NEUTRON can take? Not even a human can answer that. And of course, this varies across different organizations and networks. For example, I have a nuclear, I have a military base, I have, let's say, a hospital. So what happens if I'm under attack? I cannot just shut down everything. Thank you for your attention.
Questions?
On what?
The task graph in this particular slide.
Oh, yes. This one?
No, this one. Where you show the example of the SMTP.
Here?
Yes.
Yes.
Okay. So my question is that here there are many types of communication. Let's say SMTP.
Yeah.
There are also some implied communications that are there. Okay. So for example, there might be an ARP protocol, or maybe there is a DNS. So how are you capturing those implied communications? And moreover, some of those, depending on maybe configurations, if you look at the various RFCs for protocols, there might be some optional communications. Exactly. So how are you capturing those?
Very good question. So those the definition and the implementation of the network protocol itself will be captured by the communicator from the protocol sequence graph.
As we mentioned earlier. So it's this graph that I mentioned here, which essentially one is required to provide very detailed information on how the protocol events will span out during during the communication itself. So all those all those things that are in the other RFC needs to be in those graphs. And then the policy generator will take all those things into consideration and translate them into proper rules. Yeah. Mm-hmm. Yeah. For sure, yes. So the protocol sequence graph is part of our static policy. So usually what happens with the static policy, what we are expecting as input is that somebody has to, an expert, will have to come and define this graph. And then, of course, based on the application that we have, we will know precisely what needs to happen.
like you said very nicely, the sizes are specified. But when I'm implementing my own application, I use whatever covered this RFC, and this needs to be on this graph. This is how essentially we are capturing all those requirements. So if you specify the RFC using the graph, and the API that we provide and the policy generator will take care of it. That's the one limitation, the one needs to provide those things.
One more question. Can you put the slide on the evaluation?
Yeah.
Yeah. Okay. So my question. So can you explain? I mean, are you assuming any particular structure of the network? I mean, so for example, you have outlined number of hosts, but are those during evaluation? Are you assuming that those nodes are connected in a particular order?
No, we are adding them randomly.
Random?
Yeah, completely randomly, because we wanted to see, how things will span out during the experiments. It was completely random.
And in this one, what is the other nodes called?
Yes. So this is so basically, like I said, communication requirement graph. So when we define the network topology, you have nodes like the internet, which is outside of our control. So essentially, this one is kind of living, probably maybe from student, but it represents the internet.
It's something that we cannot control. That's why it says other nodes.
So when we are at it, I had a quick question. So this is like some kind of a simulation result?
Yes. So yeah, those are simulation results, and basically it's
The real performance actually of the generator in sport based on this randomized input, which comes to be very large at some point. Yeah.
Because to simulate it will also depend on the kind of environment.
Yes, that's very true. It really depends on how is our network. So from what I've seen in my experience, usually networks are not this complicated. So we would use, for example, backbones and stuff like that. But what we did is
Actually, we create very densely connected networks to see how this will scale and stuff like that.
Okay, so questions from online participants? Okay, so if there is no question from online participants, we'll take one last question from offline participants.
Thank you for the presentation. So also on this slide, how does execution time compare with other traditional methods or like other architectures?
architectures of
like to finish the same goal, to do the similar things as NEUTRON does.
So that's a huge challenge, because this work, so the way that, so we have implemented everything from scratch, and even our conception of the input, using graphs, there's no other tool that can do the same thing. Because the way that we envision things is that one needs to provide those requirements in a very high level, not technical level, and then leave NEUTRON do all the technical work. So we couldn't essentially combine it. I mean, to the best of our knowledge, we couldn't find any other tool that can do the same thing and encode the same information. Keep in mind that this framework also has a lot of semantic information as well that is not perhaps captured by other tools. That's why we didn't perform a comparison, but this is very, very nice idea for future work if we find such a tool. Yeah.
Thank you.
You're welcome. Yeah.
Okay, so then let us thank the speaker for the wonderful talk.